The nature of light has puzzled scientists for centuries, sparking debate and confusion that gradually transformed our understanding of physics. Newton's particle theory of light. In the late 17th century, Isaac Newton proposed the corpuscular theory of light, suggesting that light consists of extremely small particles or corpuscles, emitted from light sources. He said that they travel in straight lines unless they hit something. This idea was derived from Newton's mechanical worldview, where natural phenomena were explained using the laws of motion and force. Newton's theory explained reflection of light by stating that corpuscles strike a surface and rebound, obeying physical laws. The angle of incidence equals the angle of reflection. For refraction, he explained that when light corpuscles enter a denser medium, they experience an attractive force at the boundary. This force increases their speed and bends their path towards the normal, providing a mechanical explanation for Snell's law. Newton also used his theory to explain color. He proposed that corpuscles came in different sizes, with each size corresponding to a different color, red light being larger while violet being smaller. The perception of color in Newton's view depends on which type of corpuscle was interacting with the eye. However, the theory encountered difficulty in explaining diffraction, where light bends around obstacles or through narrow slits. Newton attempted to preserve the particle model by suggesting that corpuscles are deflected slightly by unknown forces near the edge, a phenomenon he called inflection. He believed this bending could mimic observed spreading of light, though he could not provide a mathematical explanation for it. Despite these issues, Newton's reputation and the strength of his mechanical reasoning allowed this theory to dominate scientific areas and identities throughout the 18th century. At the time, experimental tools were not precise enough to fully test or disprove the finer predictions of his theory. Another competing theory was Huygens' wave theory. According to Huygens' theory, every point on a wave of a light acts like a little source of new waves. These smaller waves spread out in circles, similar to how ripples spread across the water when a stone is dropped in. Light was thought to spread out as overlaying circular waves, bending around obstacles and through slits. This idea helped explain how light behaves like a wave, especially how it moves around objects and through openings. Huygens' model also explained diffraction in a way that made sense. He talked about how light bends at edges and interference where waves overlap. When waves meet, they can add together to make bright spots, called constructive interference, or cancel each other out, leaving dark spots, called destructive interference. Huygens' theory saw color not as a property of particles, but as a result of different wavelengths of light. For example, red light has a longer wavelength and blue light has a shorter wavelength. This idea lined up with the fact that different colors refract or bend by different amounts when passing through a prism, forming a rainbow spectrum. It supported the idea that color is a wave phenomenon. He said light would slow down when entering a dense medium, causing the wavefronts to compress and bend towards the normal. This explained refraction more accurately than Newton claimed that light sped up due to surface attractions. In 1801, when Thomas Young's double-slit experiment revealed a clear interference pattern that could only be explained if light behaved like a wave, the overall belief that light were a particle was challenged and shifted scientific opinions towards the wave model. Later, more scientists came and deepened this understanding. Austin Jean Fernand and James Clerk Maxwell. Fernzel was one of the first key scientists who developed the mathematical formulas that describe how light behaves, especially for interference and diffraction. And Maxwell's equation showed that light is an electromagnetic wave unifying electricity, magnetism, and optics. This is the inquiry question, aim, and hypothesis of these experiments. Our first experiment focuses on demonstrating the wave nature of light using a double-slit setup. The core of this experiment involves shining a laser light through a diffraction grating, which produces a pattern of bright and dark fringes on a screen. As mentioned before, this pattern arises due to interference, and diffraction being constructive and destructive interference. By measuring the positions of these bright fringes and using the grating equation d sine theta is equal to m on lambda, where m is the maximi number, lambda is the wavelength, and d is the spacing between slits, we can calculate the wavelength of the laser light. The ability to calculate a specific wavelength based on the interference pattern is a direct evidence of a wave nature of light. This is because interference patterns can only be explained by waves. Particles traveling in straight lines would create shadows or simple light spots, but would not create the regularly spaced bands of light and dark we see here. We calculated the split spacing by taking the inverse of the number of lines per millimeter on the diffraction grating. Although this value is provided on the grading card, performing the calculations ourselves helps reduce potential errors, since the laser we use is very accurate. Having precise slit spacing is important for obtaining reliable wavelength measurements. Since tan and sine are close angle approximated, we can use tan theta's value to find theta, and then use that in sine theta. Using the formula m lambda is equal to d sine theta, we can create a linear graph of y is equal to mx plus b graph, where sine theta is equal to lambda multiplied by 1 on d. In this case, lambda or wavelength is the gradient. Now we can use two random points on the line of best fit, and we can figure out the gradient, which in our case was 632.62 times 10 to the minus 9, with only a 0.0284% error. The fact that the wavelength calculated from the pattern closely matches the known value for the laser confirms that the observed pattern arises from wave interference. Historically, this kind of experiment was vital in shifting scientific understanding away from the particle-only theory of light towards the wave model. However, Young used the sunlight, which has all wavelengths, so it would have been harder for him to differentiate between the fringes due to overlap. Using a monochromatic laser helped to negate this, and using more lines per millimeter to further the diffraction. This is because the spacing between the lines d decreases according to the grating equation d times sine theta is equal to m lambda, causes the angle of diffraction theta to increase for a given wavelength lambda and order m. Therefore, the diffraction pattern and wavelength derived from it proves that light cannot just be a particle and must behave as a wave in this context. Using a simulation to confirm our data, we can see that it is very accurate. In our experiment, the distance between the diffraction grating and the screen was only 0.382 meters, which is quite short compared to the 5 meter setup used in the simulation. Because the position of the bright fringes depend directly on this distance, we could not directly compare our raw measurements to the simulated data. To fix this, we scaled up our fringe position measurements using a simple linear ratio as seen on the screen. This works because the diffraction angle stays constant, so increasing the distance to our screen just stretches the pattern outward proportionally. After scaling, our experimental fringe positions lined up closely with the simulation, confirming that our setup and measurements were consistent and reliable. After doing this, our value was 1.7 meters, which is very accurate to the simulated data. Our second experiment talks about Heinrich Rudolf Hertz's idea of the photoelectric effect. He was doing experiments in 1887 on light, however could not explain the photoelectric effect using the wave theory of light. According to classical physics, increasing the intensity of light, no matter its frequency, should eventually provide it with enough energy to eject electrons, but it didn't. The problem remained unsolved until Albert Einstein resolved this by proposing that light also behaves like discrete particles called photons, with energy dependent on frequency. This dual wave particle nature of light challenged classical physics and laid the foundation for quantum mechanics, a new field that reconciles these contradictory behaviors. The photoelectric effect is a phenomenon in which electrons are emitted from the surface of a metal when it is illuminated by light of sufficient high frequency, such as ultraviolet or blue light. This emission of electron creates a current in the system. This effect provides compelling evidence that light behaves as a particle photon, each carrying discrete energy. The experiment involves a photoelectric tube or photocell which contains two main electrodes inside a vacuum-sealed glass tube. The cathode is a clean metal surface that emits electrons when exposed to light with a frequency higher than a certain threshold. For us, this was cesium. Opposite, the cathode is the collector, or anode, a metal piece that collects these emitted electrons. The electrodes connect to an external circuit and an ammeter to measure the photoelectric current generated by the electrons, and a variable voltage source capable of applying an opposite voltage between the collector and emitter to control electron movement. The stopping voltage is a variable reverse voltage applied to oppose the motion of the photoelectrons emitted from the metal surface. As stopping voltage increases, fewer electrons have sufficient kinetic energy to overcome this opposing electrical field, causing the photoelectron current to decrease. At the stopping voltage, the current drops to zero because even the most energetic electrons cannot reach the collector. This condition is described by the equation Ek max is equal to hf minus phi. H is Planck's constant, f is frequency in the incident light, and phi is the metal's work function. Measuring stopping voltage as a function of light frequency allows direct determination of the relationship between photon energy and electron kinetic energy. The photoelectric effect demonstrates that the energy of emitted electrons depends on frequency of the incident light rather than its intensity. As seen in the formula, E is equal to hf. This energy is critical as it determines if a photon can eject an electron from the material surface, this being the work function, or phi. Experiments revealed a threshold frequency below which no electrons are emitted, no matter the light's intensity. Furthermore, the kinetic energy of emitted electrons is determined only by light's frequency, supporting the idea that light consists of discrete energy packets. This evidence confirms the particle nature of a light in this phenomenon, contradicting the wave-only description. In the photoelectric equation, we can see that the gradient is the h part of the equation, so we are trying to find that. We can find m by using 2 points on the line of best fit, so h is equal to gradient multiplied by e, which in this graph gives us the constant of h is equal to 5.3 times 10 to the negative 34. The work function is 2.05 times 10 to the negative 13, and the threshold frequency being 3.87 times 10 to the negative 14. The expected value of Planck's constant and the real value shows approximately a 20% difference in error. This discrepancy is expected in typical high school level photoelectric effect experiments. However, removing the outlier of green light gives us the constant value of 6.268 times 10 to the negative 36, which is much closer to the expected value of the constant, being about 5% error difference. The simulated photoelectric effect data produced values that were significantly closer to the accepted constant than the initial experiment's results, with only a 0.3% error using simulated data for cesium. The calculated Planck's constant as 6.646 times 10 to the negative 34. Nevertheless, both datasets support the key trend predicting by the photoelectric equation a linear relationship between frequency and stopping voltage with a non-zero frequency threshold and a slope proportional to Planck's constant. The simulation enhances confidence in the model, while the experimental data highlights the practical limitations in measurements. For accuracy in experiment 1, our calculated wavelength closely matches the known value of the laser light with only a 0.0284% error. This indicates that our measurements and calculations are highly accurate. We performed this experiment 3 times and used the average of these results to reduce random errors. Repeating trials ensures the results are consistent and reliable. The experiment effectively tests the wave nature of light using well-controlled variables such as fixed distance, stable light source, and careful measurements of fringe positions. This makes our results valid for supporting the wave model of light. In experiment 2, the experimental value for Planck's constant had about 20% error compared to the accepted value, which improved to around 5% after removing the green light's outlier. This shows limited accuracy, likely due to the measurement error and experimental limitations. The experiment was only performed once, reducing reliability. Repeating trials and ensuring consistent conditions would improve confidence in the results. The simulation data shows much better reliability with a very low error. The experiment effectively tests the relationship between stopping voltage and light frequency, supporting the photoelectric effect theory. However, some external factors like light intensity control and equipment calibration could have affected the validity. Small misalignments of the laser, diffraction gradient, or screen can shift or blur the interference pattern, affecting accuracy in the double-slit experiment. Measuring fringe distances and screen gaps precisely is tricky and can introduce errors. Environmental factors like vibration, stray lights, may also distort the pattern. Lastly, imperfections in diffraction gradient itself can also cause inconsistent results. This was limited by calculating the actual distance of the splits. In the photoelectric effect experiment, fluctuation in light intensity or unwanted ambient light can affect the photocurrent readings. The stopping voltage might be incorrectly recorded if the voltmeter or power supply is unstable or precise. Cesium photocathode surface could degrade or be contaminated, lowering electron emissions. Also, having only a limited number of light frequencies reduces the accuracy of calculated constants, like Planck's constant. The experiments conducted demonstrate the dual nature of light. The interference pattern in the double-slit experiment provides measurable evidence of light behaving as a wave, supporting Huygens' theory and confirming properties such as diffraction and interference. In contrast, the photoelectric effect reveals how light behaves as a particle with quantized energy that depends on frequency, not intensity, seen through the formula for a photoelectric effect. This behavior contradicts classical wave predictions and leads to the development of quantum physics. These experiments highlight the limitations of classic models and the need for quantum model of light, where light is understood as having both wave and particle characteristics depending on how it's observed. The duality is now fundamental in modern physics and has driven advancements in technology such as lasers, solar panels, and quantum computing.